What's up guys, it's me. I just wanted to thank you all for getting this channel to 10,000 subscribers. 10,000 people aren't actually watching every upload of mine, which I guess is unfortunate, but that's okay. So, to the 7 people consistently watching my awful content, I'll be teaching you guys something very special for this subscriber special. Bezier curves. So, what are Bezier curves? Well, say I have a grid and a few points. With these points, a Bezier curve would look something like this. So, a Bezier curve begins at the first point, ends at the last point, and the rest of the points in between influence it. Let's draw another curve for the sake of example. I'll only give this one 3 points. Again, curve goes through the first and last points, and the rest in between influence it. If I wanted this curve to be, I guess, curvier, I'd just yank this point up a bit, and now my curve would look like this. Not accurate drawing since I'm doing them freehand, but I'm sure you guys get the idea. So, given a set of control points, how do we even calculate the curve? Well, there are actually 3 ways of computing Bezier curves: nested linear interpolation, summing Bernstein polynomials, and midpoint subdivision. I'll start with the sum of Bernstein polynomials. So, what's a Bernstein polynomial? I don't really want to go too into it since this video isn't about them, so I'll just give you the necessary info. b di of t is equal to di times 1 minus t to the power of d minus I times t to the power of I. This is a Bernstein polynomial. D is the degree of the polynomial, I is any number from 0 to d, with d being greater than or equal to 1, and t is just a variable. Most of this polynomial should be fairly straightforward, unless you've never seen this before, which is a binomial coefficient. If you see one of these, just know you can solve for it like this: d factorial over I factorial times d minus I factorial. The exclamation point stands for factorial, so I'll just give you a quick example of that. What's 5 factorial? Well, that's just 5 times 4 times 3 times 2 times 1, which equals 120. Basically, you just take the number you were given, then multiply it with every number below it till you get to 1. Now that we know what a factorial is, we can now solve binomial coefficients. So, say d is 5 and I is 4. Well, that just means 5 factorial over 4 factorial times 5 minus 4 factorial. That equals 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1, which equals 120 over 24, which equals 5. Also, if you have a binomial coefficient where the bottom number is 0, like this, it always equals 1. Alright, now that we know what a binomial coefficient is, we can start evaluating Bernstein polynomials. We'll do examples with a degree of 2. Let's start with I equals 0. b20 of t equals 20 times 1 minus t to the power of 2 minus 0 times t to the power of 0. That just equals 1 times 1 minus t to the power of 2 times 1, which equals 1 minus t squared. For I equals 1, we have b21 of t equals 1 times 1 minus t to the power of 2 minus 1 times t to the power of 1. That equals 2 times 1 minus t to the power of 1 times t. That just ends up equaling 2t times 1 minus t. And finally, for I equals 2, we have b22 of t is equal to 2 times 1 minus t to the power of 2 minus 2 times t squared. That equals 1 times 1 minus t to the power of 0 times t squared, which just equals t squared, because 1 minus t is to the power of 0, and anything to the power of 0 is just 1. Once we're done, we'll end up with 3 polynomials. Again, we're doing the sum of Bernstein polynomials method, so we'll be adding these up to get our Bezier curve. Here's the general formula. We have a sum with I starting at 0 and ending at d. Inside the sum, we have the Bernstein polynomial times p sub I. P sub I is a control point, so if we have 3 points, they'd be p sub 0, p sub 1, and p sub 2. Alright, let's see this method in action. Let's do a quadratic Bezier curve. Quadratic means it has a degree of 2. That also means we have 3 points. The number of control points is always degree plus 1. Let's say our 3 points are 0, 0, 0, 1, and 1, 1. I'm sure you have a general idea of how the curve will look, but let's get an accurate drawing with our sum of Bernstein polynomials. Conveniently, since our degree is 2, we can just use the polynomials we got earlier without having to do the work again. Anyway, by plugging these polynomials and points into the general formula, we get 1 minus t squared times 0, 0 plus 2t1 minus t times 0, 1 plus t squared times 1, 1. I guess it looks a bit awkward with the point notation, so let's split it up. 1 for x and 1 for y. X equals 1 minus t squared times 0 plus 2t1 minus t times 0 plus t squared times 1. y equals 1 minus t squared times 0 plus 2t 1 minus t times 1 plus t squared times 1. Let's simplify these two equations. These two parts are multiplied by 0, so they cancel out, and you're just left with t squared. This part cancels out, you distribute the 2t here, and you get 2t minus 2t squared minus t squared, which ends up equaling 2t minus t squared. Okay, so we have t squared for x and 2t minus t squared for y. That's our Bezier curve, a parametric equation where both the x and y are represented by another variable, the t, also known as the interpolant. All you need to do now is plug in values for t and plot the results on a graph. When you're plugging in values for t, make sure they range from 0 to 1. If you plug in values for t outside that range, you'll get points that still make sense, but they lie outside of the bounds of the first and last points. So let's just stick with 0 to 1. Ideally, you'd plug in all values between 0 and 1 to get a perfect curve, but there's an infinite number of values between 0 and 1, so we'll just plug in a few and connect the dots as best as we can. Alright, so I have our parametric equation on a calculator here, depicted as a column vector, but just know I'm still calculating a point. All I need to do now is plug in my values for t. Let's go with 1 over 2, aka 0.5. Okay, so we get 1 over 4, 3 over 4, which is roughly here. Now let's do 1 over 4, aka 0.25, 1 over 16, 7 over 16, that's roughly here. And finally, we'll do 3 over 4, aka 0.75. That gives us 9 over 16, 15 over 16, which is pretty much right here. If you plug in 0, you just get the first point, and if you plug in 1, you get the last. So, if we connect the dots here, we get this curve. There you have it, computing Bezier curves using the sum of Bernstein polynomials. Of the three methods, this is probably the easiest one to do since it's just using a formula, but it's my least favorite because Bernstein polynomials are a bit abstract to me. They're like a, hey, this just works kind of thing. It's also the most expensive computationally, because calculating binomial coefficients takes a while, especially when they're larger values, but there are ways around it like generating Pascal's triangle beforehand and using it as a lookup table so the computer doesn't have to do any actual multiplication and division for it, but I digress. Let's move on to the next method, nested linear interpolation. Alright, before I get into the actual numerical stuff for NLI, I'll give you a more visual representation. So, let's say I have these 4 points and I connect them like this. This is known as the control polyline. Now let's say I have that variable t again. Plugging in a value for t between 0 and 1 will move me along these 3 lines. So, let's plug in 0.5 for t. That's in the middle of 0 and 1, so we'll be here, here, and here. Now let's connect the dots we just drew. If we use t equals 0.5 again, we'll have 2 dots like this. Let's draw a line between them. Oh, by the way, these lines we're drawing after the polyline are known as shells. Anyway, if we do t equals 0.5 once again, we'll have a single dot at the center of this line. This point right here is on the Bezier curve. Let's find another point, say for t equals 0.25. That's a fourth of the way into the polyline segments, so they'd be roughly here, here, and here. Now let's draw the shells, the next couple dots at 0.25, and there's your next point. If you keep doing this, you'll eventually get the overall Bezier curve. Alright, now how do we actually compute this? Well, NLI goes a bit like this. You start out with your control points. Let's say we have 3, p sub 0, p sub 1, and p sub 2. Let's add superscripts of 0 to each of them. What you do next is pair the adjacent points together to get new points. I'll give these guys superscripts of 1. Do this until you have 1 point left, and that's your point on the Bezier curve. Call it gamma t. If we were to draw another set of points to represent this little table we made, you'd see the first column is our control points, the second is the points between them, then the final column is the 1 point between the ones from the second column. The math behind combining adjacent points to get a new one goes like this. 1 minus t here, and t here. You multiply 1 minus t with the top point, t with the bottom point, then add the two together. So, if I were to generalize this, you'd have pi minus 1 is equal to 1 minus t times pi minus 1 I minus 1 plus t times pi minus 1 I, with I greater than 0 because you don't want negative indices here. Alright, let's do an example of this. Let's go with the 3 points we used in the Bernstein method, just to show you we'll get the exact same result. 0, 0, 0, 1, and 1, 1. I'll do t equals 0.5, 0.25, and 0.75 as well. This part does get a bit monotonous since it's just using that generalized formula over and over again, with different values plugged in. Just use a calculator, or better yet, program the algorithm. Also, no, those aren't binomial coefficients, they're our points, but I wrote them out in vector notation to conserve space on the page. Okay, when you're done with the calculations, you'll get 1 over 4 3 over 4, 1 over 16 7 over 16, and 9 over 16 15 over 16. Those values should sound pretty familiar because they're the exact same values we got from the previous method, so this is another valid way of calculating Bezier curves. Of the three methods, this is probably my favorite. It's pretty easy to understand when you're learning it for the first time, and it's probably the easiest one to program. Or at least, I think so. Anyway, let's move on to the final method, midpoint subdivision. Generalizing it is a bit convoluted, so I'll just jump straight into an example, with the same 3 points we've been using, of course. We're going to start by making a column of our control points. What we do now is take the adjacent points and calculate their midpoint. So, how do you get a midpoint? Well, the formula for that is x1 plus x2 over 2, y1 plus y2 over 2. Okay, we have this little triangle now. This final point here is on the Bezier curve, so store that somewhere else for now. This next step is what makes midpoint subdivision pretty unique. What we do next is make this same table, but for the top 3 points and the bottom 3 points. So, for the upper edge table, we'd have 0, 0, 0, 1 over 2, and 1 over 4, 3 over 4. For the lower edge table, we'd have 1 over 4, 3 over 4, 1 over 2, 1, and 1, 1. Okay, we have the two tables done. What now? Well, you take the 2 results you got for each and store them for later, but you can keep computing more points. Just take the upper and lower edges of both tables, make tables out of those, then you can make more tables out of their edges. It goes on forever. You just have to specify when you want it to stop. Anyway, as you can see, these 3 boxed points are, unsurprisingly, the exact same points we got from the previous 2 methods. So, that's midpoint subdivision. I don't like it as much as NLI, but that's just because it wasn't too intuitive when I learned it for the first time. Objectively speaking though, it's probably the best method from an efficiency standpoint. If you made a program with these 3 methods implemented and generated a Bezier curve with, say, 1,000 control points, midpoint subdivision calculates it way faster than Bernstein and NLI. It's a much more scalable solution, basically. So yeah, that's Bezier curves and how to compute them. This is probably my favorite topic in math. Not only is it really simple to compute these curves, but they're just so useful. They're used in computer graphics like 3D modeling and animation. If you're making a video game, you could probably use them for a variety of things. It's how the pen tool in Photoshop works. Hell, the guy who discovered Bezier curves used them in car manufacturing. It's math that's actually very applicable. And that's when math is at its best, when there are actual reasons to use it. Anyway, I actually forgot this was a subscriber special. To the people subscribed, thanks for subscribing. To the people actually watching this, thanks for watching. I really hope you learned something from this. See you guys in the next video.